Do you see my screen?
Yes, we see.
Hello everybody, my name is Panagiotis. I am a mechanical engineering student at the University of Western Macedonia here in Greece. And today I'm going to present you our work in chaotic agent navigation and achieving uniform exploration through area segmentation. I'm going to start by talking about the motivation behind chaotic path planning and the objective of this work, and continue with the path planning system and the area segmentation technique that we used as an optimization technique. Then I'm going to present the simulation results and conclude this presentation and have some discussion about some future research ideas. So I'm sure that many of you are familiar with chaos applications. One of them is path planning, and path planning itself has many applications as well. Some of them are floor cleaning devices, firefighting devices, but some more relevant are surveillance of terrains, terrain exploration, and patrolling. The goal here is to generate unpredictable motion trajectories for an agent. For example, in situations where the agent is under potentially hostile environment and it's targeted by an adversary, it must maneuver in ways that it could confuse the enemy and could not be predicted, while also maintaining an efficient exploration of a given space. Also, for example, if the agent is defensive and it surveils a specific area, if the motion of this agent can be predicted by the adversary, it could be exploited, and the adversary could avoid our agent. So this work builds upon previous works by considering a limitation in the possible movements of the agent to try and eliminate sharp turns and eliminate turns that are like 90 degrees or more. So it's making the path smoother, and thus it makes it applicable to a real robot. Also, it is a chance to improve the coverage percentage of a given area and the uniformity of the coverage inside the area, but most importantly, the consistency of achieving that coverage. This was achieved by segmenting the given area. To create the navigation commands, the rainy map was used as a chaotic source, and K was chosen to be 19.99. The trajectory of the map can be seen at the bottom of the slide for K 19.99, and we can see also that the map exhibits constant chaotic behavior in respect to each parameter, which can be verified by the Lyapunov's exponent diagram for any K over 1. So now, the robot has 8 possible directions and 8 possible orientations. The relation shown on the right-hand side of the slide generates numbers between 0 and 7. And as we can see in the histogram at the middle of the slide, for 20,000 iterations, this relation generates uniformly distributed these numbers. If there is an application that bias is required, the relation can be accordingly modified. So at the beginning, we thought of letting the robot free to move without restricting its possible movements. But then we saw what I said before, that the path was really sharp and made it difficult to apply that idea to a real agent. So we restricted the possible movements to front left, and front right. And we introduced a variable that determines what are the 3 possible movements. This variable is the orientation. As you can see on the left-hand side, that if the orientation is 0, the 3 possible movements are 7, 0, and 1. And if the orientation is 3, for example, the possible movements are 2, 3, and 4. The orientation itself changes according to the previous movement of the robot. If the previous movement of the robot was, for example, 0, the orientation remains 0. But if the previous movement was, for example, 1, the orientation changes accordingly. Also, the algorithm is such that in each iteration, the robot is prompted to make a move. If that move is not allowed, for example, if that move prompts the robot to cross a boundary, the robot stays at the same place and changes its orientation and waits for the next allowable move. This is similar to mirror map. So now to optimize this technique, we divided the area into equal sub-areas and we introduced a 100 by 100 area to be explored. We divided that area into 4 and 16 sub-areas and examined 2 and 4 different patterns for each approach respectively. Regarding the threshold of moving from one sub-area to another, 2 approaches were considered. The first one was giving the robot a coverage target value to achieve, and then move on to another sub-area. And here the main evaluation parameter is the steps needed to achieve this coverage. And the second approach was giving a specific amount of steps for the robot to perform and distribute between the areas. And the coverage itself is now the main evaluation parameter. So for the simulation that I'm going to show now, they all regard the second type of threshold because having as an evaluation parameter the coverage itself is more easily interpreted than the steps needed to achieve a specific coverage. And also one of the patterns for the 16 sub-area case and 4 sub-area case are presented. Also, as you can see, we introduced 2 more variables, the mean visits and mean visits of visited cells, which can evaluate the efficiency and the consistency of the path. Here you can see a demonstration of the robot's path. We can see that the path is smooth and visits almost the whole area, but we can also see that there are some areas that are not visited and some others that are visited multiple times. This can be seen in the simulations too. We can see for 5,000 steps that the coverage is about 35% and the mean visit is about 1.4. And for 10,000 steps, the coverage goes up to about 60%. For 15,000 steps, we can see that the coverage is about 76% and the mean visit is about 1.97. Note that for all the simulations, the initial position was the bottom left cell and the initial orientation was random. We can see both in the third simulation and on the other 2 that the coverage is not uniformly distributed between the area, and there are some areas that some cells rather say that are visited up to 10 times and others that are not visited at all. That's why we thought of dividing the area to 4 and 16 equal sub-areas. Now you can see a demonstration of the 2 patterns for the 16 sub-area case. We can see again that the robot covers almost all the area, but now we can see that the coverage is more uniformly distributed between the area. This can be seen also with the simulations. In the parentheses with the red-orange color, you can see the values of coverage, mean visits, and mean visits of visited from the first approach with the one whole area case. And we can compare them directly with the segmentation technique. We can see for 5,000 steps that the coverage increased about 4%, but the mean visits of visited decreased. That's also true for the 10,000 steps where the coverage went up to 61.6%, and for the 15,000 steps case. Here we can see more clearly that the coverage is more uniformly distributed between the area, and the thing that is more important is that the coverage was achieved more consistently than before. This can be seen better in that graph. We can see with the blue lines the 16 sub-area case, and with the red lines the one whole area case, and the dashed line denotes the minimum and maximum performance of the agent. We can see that the mean visits of visited for the 16 sub-area case are constantly lower than the one whole area case, and also the difference between maximum and minimum performance is decreased. This is true for the coverage itself. We can see that for when using the segmentation technique, the coverage is constantly higher than the one whole area case. But the thing that I said that it was more important is that the coverage was achieved more consistently than before. We can see that the deviation between maximum and minimum performance when using the segmentation technique, it's much less than it was for the one whole area case. Now, to conclude this presentation, a chaotic navigation algorithm was developed, which had the desired chaotic behavior. Also, restricting the motion of the robot led to a smooth path, which makes the system easily applicable to a real robot. And using the segmentation technique also increased the coverage itself and covered the area more uniformly. But most importantly, as I said, the coverage was achieved more consistently. So for the future, there are several differentiations that can be added to the system and also many problems that can be considered for further study. For optimizing this existing system, there are more techniques that can be used, such as pheromone, and which can be directly combined with the algorithm that we have. Also, introducing some obstacles and unpredictability to the environment will make the system applicable to a larger scope of applications. And the experimental realization itself is something that should be studied so we can test the performance of the agent in a physical environment. Also, all of the above can be considered while using multiple agents and 3D environments, for example, for UAV applications. And there are some more applications, some more studies that can be done on that, like the system in non-physical environments too, such as in image encryption. Here are some indicative references, and now I want to thank you for your time and attention.
Panayotis, thank you very much for your interesting presentation. And now we have time for questions. Please, you're welcome to ask questions.
Thank you.
Please, colleagues, you're welcome to ask questions. Okay, if nobody asks, I will do this.
Can I ask?
Yes, please, Igor. You're
Good day. Thank you for an interesting presentation. I have the following question. Do you compare the road distance with your method, chaotic method, with regular one? I think it will be more bigger when we use chaotic method to cover target area when we use regular one. When, for example, when we use unmanned aerial vehicles to cover target area, and in this case we have restriction to flight time for each unmanned aerial vehicles, and in this case when we use chaotic approach to cover target area, maybe necessary to use more amount of unmanned aerial vehicles because the flight time is restricted and the distance of road to cover this target area is bigger when we use regular methods to cover.
So what's the question? I didn't understand.
We consider the chaotic method, and when we use the regular method to cover target area, the road, total distance of road will be bigger when we use regular road.
Okay. Okay.
Do you consider, do you compare with distance with your method and regular method?
So some physical, in that algorithm, physical parameters like velocity and distance and that were not considered, but I understand that you say when using not chaotic path planning, but some deterministic maybe paths, you cover more distance in the same amount of time because it's restricted, the flight time is restricted.
Yeah.
Okay.
We are covering more area, right? Exactly.
Yeah. Okay. In that case, it's another approach because the approach that we have using chaotic path planning is trying to avoid predictable motions, so that cannot be exploited by an enemy or an adversary. Using something that can be foreseen by an adversary, maybe it has a pattern or it's periodic or even it can use the code to know what's the path. Then the adversary could know what's the path of our agent and get exploited. So that's why we used chaotic path planning to do so.
Thank you for your interesting report. Thank you very much.
Thank you.
Dear colleagues, some other questions, please. You're welcome. If nobody has questions, I can ask one simple question. What kind of features do you use for segmentation? Is it color, texture, something else?
Sorry, what kind of features did you say?
What kind of features do you use in segmentation? Color, texture, what else?
At the algorithm with the, sorry?
You can say.
Using what I understood is what kind of features are we using for the segmentation?
Yes.
And okay, by features, what do you mean? Sorry.
For instance, color, texture features.
When I believe you have to say when we are in a physical environment, that can be that features can be like color or some images that the agent may process, but this algorithm was not developed in a physical environment. But that is something that we can work on the future. That, as I said, some future suggestion that in a realization of an experimental version of this agent, we should do the segmentation using some physical features and not only boundaries in an algorithm.
Okay, thank you.
Exactly, as Panagiotis, Professor.
Do we have some other questions to Panagiotis?
If I may add a single note right here, it's just that exactly as Panagiotis said, in a physical environment we can have exactly the same chaotic technique, but maybe the segmentation, for example, we can consider some Delaunay triangulation, for example, in a physical environment, and then take each one of these triangles and apply the exact same technique. So it can be adapted to different segmentation techniques. Yes.
Lazarus, thanks for comments. Okay, I see that we do not have more questions, and thank you for a very interesting presentation. And let us come to the next.